Hey guys, you can open your notes to this page and we are going to start doing some of the calculus of polar. We're going to start off with derivatives of polar curves. Before we do that, little review because you're going to be having to do a little conversion, not a whole lot in here, but just a little review of our conversion between rectangular and polar coordinates. Let's go draw a right triangle with an angle theta, a radial of r, moving x and y. And remember our relationship for getting x in terms of r and theta is x is r cosine theta, which we've already derived, so I'm not going to do it again. And y is r sine theta, and these are the two you're going to be using the most in this section, but just to remember the other ones to keep them fresh. We also know that if need be, we could say x squared plus y squared is r squared. Or equivalently, r is the square root of x squared plus y squared. We can say that tangent of theta is y over x, or theta is tan inverse y over x. And we've got some conversions. So we are going to be finding today dy dx, and it's what it's always been for us, the slope of the tangent line. Whether we were in function mode and we were looking for the slope on this parabola, or in parametric mode and we were looking for dy dx right here, or now in polar mode where we might have one of these, we're still going to be getting the slope of the tangent line. So how do we do that? It's really similar to how we did it when we were in parametric. Remember for parametric, we said that dy dx was equal to dy dt. We had that time parameter over dx dt. In polar, it's very similar, only our parameter or our unit of change isn't the time or the t, it's an angle or a theta. But formulaically, it looks very similar. It looks like this: dy d theta, dx d theta. The only issue is we need to, like in parametric, we'd have to say x equals, and it was some function of time. Now we need x as some function of r and theta. Well, we already have up here how that relationship works. X is r cosine theta, and y is r, sorry, that's not a good r, and y is r sine theta. So for example, if I were doing this polar curve, and you should know what that makes from yesterday. Remember when you mess in there with that theta, we make those rose curves. Because that is even, it would be a rose curve with how many petals? Exactly, 4, because you double it if it's even. So that's a rose curve with 3 petals. I think what I'd like you to do is go graph it. So I'm going to give you a minute to get your graphing calculators out. I'm not going to go graph it, but I just want you to see that. So again, take out your graphing calculators, please. Make sure you are in polar mode, but you should be from yesterday. And go enter r equals sine 2 theta. And then remember, so you can see it in full, hit zoom fit followed by zoom square. And you'll get a nice polar curve that looks like, I believe it starts here, goes like this, goes here, then goes over here, and then goes over here. And that's r as a function of theta. Well, we want x. How far over and how far up an I? That's my x and y, because I want to do dy dx. And in order to do that, I need to convert them. So remember our conversion. X is r cosine theta. Well, here's r. So I do sine 2 theta cosine theta. And y is r sine theta. So I do r sine theta. And so now I have x and y in terms of theta. So to take the derivative, it's actually a formula, but you know me, I don't like to use formulas, so I would challenge you to avoid a formula if you can. I will derive it for you and then tell you I wouldn't use it. So let's go up here. On the top of our fraction, because dy dx is a quotient, on the top we do the derivative of y with respect to theta. So we're going to do the derivative of this product, which means product rule. So we're going to do first r, d second would be cosine theta, plus second function, which is sine, times the derivative of the first. And you might say, well, the derivative of a constant is 0. But remember, r is not a constant. That radius is a function, and it is changing. So it would be r prime, or you could write dr d theta. On the bottom, I do the same thing. I do first, in this case, it would be r d second plus second d first. And that's the formula. But who's ever going to remember that? So you'll notice over here on the next page, I have that formula written right here. And you can go ahead and use it, but I would be pretty certain that you're not going to remember that in 5 months. But if you can just create your own y of theta and x of theta first, and then take the derivatives separately, then you can just write y prime over x prime, and you'll have dy dx, which seems confusing, but when I do one, it's actually not. So what I'm telling you is, what I would suggest you do on one like this is just create your own x and create your own y. Do their derivatives separately. So and I like to do dy d theta first just because it's going to go on the top of the fraction, so it's organized nicely. But I would just say this right here is first d second plus second d first. And the derivative of sine 2 theta would be cosine 2 theta times 2. And it's getting a little messy, but you get the idea. Just create your own x and create your own y, and do similarly take the derivative of x with respect to theta. Just use the product rule on this. And then when you're all done, your dy dx will equal the quotient of those. And that doesn't require memorizing a formula. So let's go do one so you can see what's going on with it. So I did put some double angle identities on here in the event that you need them. If you don't use them. I like to avoid the trig identities if I can, but sometimes they're necessary. Like you're going to get stuck and you're going to say, I've got 2 sine cosine theta, but if I could get it all in terms of sine, it'd work. So you'll use that one, and you're pretty used to using those. So here is our function, and we're going to find dy dx at pi halves. So I want to know the slope of the tangent line to this curve at pi over 2. Well, it'd really help if I knew what the curve looked like, and that's why we talked about the graphing yesterday. Do you have to graph them? Only if I ask you to. On the AP exam, they graph them for you quite a bit. But let's see if we can kind of sketch out this graph without using our calculator. We first of all should know, and again, I wouldn't even make a table of values. I just kind of think it out until you're like, oh yeah. You should recognize the pattern of that. That is not a rose curve because we're not in there messing with theta. It's not just a single circle because we have that 2 plus 2. But remember, they're tied. So you're going to get a butt graph on this one from yesterday. The only thing is, well, how do I tilt it? So what I do is I just kind of go in here, and I let theta be 0, and I would have 2 plus sine 0, which is 2. So I know I'm going to start out at 2 on my polar axis. Then I'm just going to go see what happens at where it's its most, because when it's like one of those butt graphs, you know, the max, you know where to put the bottom. Would that be the top or the bottom of the butt? I don't even know. Anyway, at pi over 2 is where that's going to max out, because that's where you get sine theta equaling 1, the most it can be. So at pi over 2, it's going to be up here at 4. And then at pi, again, sine pi is 0, so you're going to be here. So you can kind of see that you're going to have that upside down y-axis butt graph. And you can go confirm that on your calculator if you want, but that's what it's going to make. What am I looking for? I'm looking for the slope of the tangent line at pi halves. Honestly, if I have a decent graphing knowledge, if this was on the AP exam, I'm like, hey, that's 0. It's a horizontal tangent line. But perhaps you have something you don't know and you need to go through the process. So we're going to go through the process of arriving at dy dx equals 0. But remember yesterday, I said you're not going to have to graph necessarily, but knowing what they look like can really ease the calculus, because now, just because I know what the graph looks like, that it's that butt and that up there at pi halves, I've got a slope of 0, I know what answer I should get. So I know my calculus needs to confirm my visual. So how do I do that? Well, I'm going to write x and y as functions of r and theta. So I am going to say x is r cosine theta. So there's r cosine theta. And y is r sine theta. The slope of my tangent line is dy d theta over dx d theta. So I'm going to do dy d theta first. And I'm not going to memorize that formula up there because we hate formulas. Well, we don't. Your teacher does, though. How is the best way for me to take the derivative of this? Sorry, you might say the product rule, and I kind of agree with you, and the product rule will certainly work, but I'm seeing that if I were to distribute that sign in and call it 2 sine theta plus 2 sine squared theta, my derivative might be a little easier, but it doesn't matter. So on the bottom for me, to take the derivative, I'm not even going to use the product rule on that. I'm just going to take that derivative as the derivative of 2 sine theta, which is 2 cosine theta. Whoops, sorry. I don't know why I have a fraction bar there. Anyway, I'm going to have 2 cosine theta plus 4, right? I'm going to bring that out front, sine theta to the first, cosine theta. And maybe you're seeing a trig identity here, but honestly, it really won't aid in anything because you're just going to be eventually plugging in a pi halves. Maybe you want to do that right now, right? I mean, you can plug, you're going to be doing dy d theta anyway, so you can know that when you do dy d theta at theta equaling pi halves, you're going to get 2 cosine pi halves, which is 0, plus 4 sine cosine, which is 0. You do know that you have a 0 on the top of your dy dx, because that's what dy d theta is. And because you know it's not the cusp, you can see it, but we really should go do dx d theta and just show that it's not. But this one you can take a couple of side steps if you really understand what you're doing. That dy d theta is going to 0 at pi halves. I'll have a 0 on the top of my fraction. I'll have a slope of the tangent line of 0. But it's not meant to be outsmarted. It's meant to take the process on through. So if you didn't think to outsmart it, or it's one that you can't outsmart, the next part of the process would be, let's go find dx d theta, because that would go on the bottom of my fraction right here. Dx d theta, and again you might say, oh, I'm going to distribute this cosine in. That won't make this one much better because you'll have to do product rule anyway. Or maybe you do a trig. There's lots of ways to tackle those derivations. I'm just going to do product rule on that one because to me that looks pretty like the way to do it. So I'm going to do first 2 plus 2 sine theta, d second, which would be negative sine theta, right? Plus second, which is cosine theta. Lots of trig stuff. These are one of the most labor-intensive sections you're going to have. Anyway, where was I? I did first d second plus second, and then d first would be 2 cosine theta. So I'm going to have a 2 cosine squared theta. It's clear to me that at pi halves, this will not go to 0 because this will, but this part of it won't. I really honestly for this question don't care what it is, I just care that it's not 0. So I know that dy dx is equal to, for this one, 0. And I knew it from the start because I knew what my graph looked like. One more. This one is, holy moly, a long one. This is the last one we're going to do. So now I'm looking for points of horizontal and vertical tangency to the graph of 2 minus 2 cosine theta. And again, although it doesn't say to graph it, if you graph it, you really get a good idea. Sometimes you can even see what your answers are supposed to be. So let's go take a look at what the graph of it would look like before we launch into the calculus. But don't grab your calculator because you wouldn't have one. So again, I know because I'm not messing with the theta, I don't have the rose curve. I know that because there's a number out front here, I don't just have a circle. I see that these two are tied. That tells me butt graph. I just need to know how to orientate that butt. So it sounds bad, but it's really, it's the way to think of it. So I apologize, but it's got to be what it's got to be. So I start out with where am I at the pole? At 0, I would be 2 minus 2 cosine 0, which is 2 minus 2. So this one starts at the pole, right here. And then again, I would find some angle to go to and along my polar axes here, an angle that's easy to take the cosine of. For me, I think I would even just, because you know it's going to make a butt, I would go to 2 minus 2 cosine pi halves, and you'd be up at 2. So you know you're going to be here. You're going to be the farthest away when cosine is pi, because that's going to be 2. So that tells you kind of where that long part of the butt is. It's going to be 2 minus 2 times negative 1. So it's going to go out here to 4. So you can kind of get the idea that it's going like that from yesterday. Oh, kind of a bad graph, Miss LaRude. But actually, it's pretty decent. I am looking for my points of horizontal, which I know I'm going to have 2 answers. I'll put them in green. I've got a horizontal tangent here. I've got a horizontal tangent here. I've also got a vertical tangent over here. I can already see that one answer to this is going to be 4 comma pi. I've also got verticals over here. So I now know I'm going to have 5 answers, and I can kind of almost even, if I had to guess at that one, I'd say it's pi thirds. I mean, I really would, is what's providing me with my one of my verticals. And so this one's probably negative pi third. I mean, you can kind of see the answers without doing the calculus, but we have to do the calc because it's what this is all about. So let's go do it. I'm going to write x as a function of theta. It's r cosine theta. So r cosine theta. Similarly, I'm going to write y as a function of theta, or y in the polar system. It's r sine theta. Next up, I am going to go find my derivatives. I can do dy d theta or dx d theta. I usually, it doesn't matter. I'm looking for vertical and horizontal tangent lines. So really remember, let's go write this down. For my vertical tangent line, dx d theta would have to equal 0. Well, dy d theta does not. For my horizontal tangent line, the top would have to be 0, but the bottom can't. Remember, when both of these equal 0, remember what that means on the graph? When both are 0, we get the cusp, so that we kind of know where that's going to happen because we can see the graph. We know at 0, 0, it's going to provide a 0 for both of my derivatives. So now I just got to go take the derivatives. Woof, done. It's a lot. This is a labor-intensive problem. This section, again, I already said that is one of the more labor-intensive. So let's go work on our vertical tangent line. I already know the answer from my picture, but let's confirm it with some calculus. I need to do dx d theta. All right, so let's go take a look at what x is and how to combat that. I could use the product rule on this. However, I do kind of like when I have the same trig function, I like to distribute it because I just think it's kind of easier to use. So I'm going to call my x, let's do it right below it, 2 cosine theta minus 2 cosine squared theta. And that derivative falls out nicely, right? When I do the derivative of that, I am going to get negative 2 sine theta. Is that correct? I believe so. I'm going to have negative 2 sine theta. And then I'm going to have minus 4 cosine theta. Derivative of the guts would be negative, so it makes that a plus, sine theta. That's what I'm seeing for dx d theta. I then want to know where it equals 0, so I'm going to factor out a -2. Let's call that sine theta. Actually, I can factor out a -2 and a sine. Let's do that. So I'd have -2 sine theta times 1 minus 2 cosine theta, right? So this doesn't affect things. So either the sine of theta equals 0, and that would occur when theta is equal to pi, or 0. All right, so I've got two candidates there for vertical tangent lines. Also, I have to find out where cosine theta is equal to 1/2. And we know that that occurs at pi thirds and at 5 pi thirds. All right, so those are my theta values. It said to do theta r because you're supposed to get the points. Before I write those points, I'm just going to wait. But you can see on your graph, this is at an angle of pi, and it would be at 4 comma pi. That would be one vertical tangent line. This one over here is the 5 pi thirds. And if you plug that in, again, you'd have to go plug that into your equation for r. So let's go back up there. When you plug, you got to go all the way back up here. When you plug in the 5 pi thirds, cosine of that is 1/2, and you're going to get 2 minus half of 2. You'll get a 1. Just trust me. Same thing when you put in the pi over 3. So those are the 3 points of vertical tangency, and you might say, why didn't you use 0? I can already see from my picture it's a cusp, and you'll see it fall out when I do dy d theta. 0's also going to be one of my solutions. So let's go up next. Ooh, I'm getting tired. I'm getting sweaty. I want to be done with this one. All right, way back up to the top. So the next thing I need to do, my dy d theta. I'm going to rewrite it down here. It's 2 minus 2 cosine times sine. So let me rewrite that. My y is equal to 2 minus 2 cosine. And again, I'm just rewriting it because this problem's, you know, you're doing difficult math when your smartboard is not long enough to contain it. All right, so let's not lose track of what we're doing. We're finding the slopes of the tangent lines. dy dx is dy d theta over dx d theta. I just did dx d theta. It gave me candidates for vertical tangent lines, and then I found the points at those thetas, and now I am going to go find dy d theta. Let's have at it. If I were to do dy d theta, I would do product rule on this. Again, I could dump the sign in, but it's going to require product rule anyway right here. So you're going to do first d second plus second d first, which would be what? 2 sine theta, right? Watch my signs here, but I think that's correct. Derivative of cosine is negative sine. It's going to make that a plus. So if I wrote that out a little bit nicer, I have 2 cosine theta minus 2 cosine squared theta, bam, plus 2 sine squared theta, bam. Here's my problem. Well, first of all, I want to know where it's 0, so let's cancel off all these 2's, shall we? Because we could divide out a 2. So I want to know where 0 is equal to cosine theta minus cosine squared theta, right? Plus sine squared theta. Well, my problem with this is I've got cosine squared and sine squared in the same problem. And if I can do this without a calculator, it means I must be able to make it better. And this is where the trig identities come into play. I would take the one that's in there the least and write it in terms of cosine. And if it doesn't work, I'd try something else. So I'm just going to go on good faith that if I replace cosine sine squared with 1 minus cosine squared theta, that maybe this will work out. If not, I try a different trig identity. So what does that leave me with? Let's clean this up. I'd have a minus 2 cosine squared theta plus cosine theta plus 1. That's still not looking very good, but you learned in pre-calculus actually that this is looking very much like it's in quadratic form. I'm going to factor out a -1 because I hate having a lead that's negative. And remember, this is 0 all the way over here. So if I were to factor out a -1, that's what has to be 0. Well, that looks an awful lot like the pre-calculus. You used to write these in quadratic form. It looks kind of like that. If I could factor this thing, I think I'm on the right track. So let's give it a whirl. Oh no, just be done. I can't. The problem's not over. The show's not over till the fat lady sings. I haven't sung yet. All right. So just like this over here would be 2x and x, and you'd make it -1 plus 1. Similarly, this is going to be 2 cosine, and it's going to be +1 and -1. And now this is super solvable because I need to know where cosine theta is equal to a -1/2. Where does that occur? At theta is equal to 2 pi thirds. Right? Now let's go back to my crappy graph. Oh boy, it's so far up there. That's right here. You can see that's right where, even on my crappy butt graph, it looks pretty good. All right. Wow. Nobody said Calc 2 was easy. They just said it was so much fun that you would dream about it at night. I'm trying to extend my page. All right. Also, that would occur at 4 pi thirds. So those are going to provide me with horizontal tangent lines. Over here, I need to know where cosine theta is equal to 1, right? Oh, wait a minute. Yes, which would imply that theta is equal to 0. Yeah, and remember we had to chuck 0 out because it occurs in both, and this provides us with a cusp on the graph. So if you were to finish this one off, you would then have to give the points. So you would have to write these in terms of r theta. So you'd have to take your 2 pi thirds and your 4 pi thirds, and you would have to go plug it back in to your original r. Your original r to determine the x coordinates. And I have so much screen here, I don't even know where the original r went. Now, if you stand back and look at that, that looks like somebody completely vomited trig onto the board. But again, the process is doable. It's just got a lot of stuff in it. So your homework is going to be worksheet number 8, and I will post that key to Schoology for you too. You guys have a good one. Bye.